Hi guys, welcome to online geometry. I'm going to do my best to explain our lessons through here, and then you can ask me questions via Google Classroom. So let's get going. So we have been working through circles, and at this point we haven't talked about segment lengths within circles. We've only focused on angles. Today we're going to look at a specific strategy that happens with chords intersecting. So looking at this theorem here, it says AE times ED equals BE times EC. I don't want you to confuse this with the entire length of the chord. Those could still be different. The pieces along it will technically be proportional. So this example explains where this comes from. We look at these intersecting chords, so segments within the circle. We have pieces along them. We want to find x. We have this piece is 2, this is 3, and this is 4. If we take those chords and create other chords, so a chord here and a chord here, we now have two triangles. These two triangles are going to be similar because we have congruent vertical angles, inscribed angles across the same arc, so therefore they're congruent, and another set of inscribed angles across from the congruent arc, so they're also congruent. So by angle, the triangles are similar. And we know with similar triangles, the sides are therefore proportional. So what I did here is I set up a proportion. I said 2 between the 3 and the 1 marking compares to 4 between the 3 and the 1 marking, the same way that 3 compares to x in this case. Simply cross multiply and solve from there. If you would like, you can always use this strategy though of multiplying pieces, like we did here, along the same chord. So 2 times x equals 4 times 3. It's up to you. Either proportion or skip right to this point. Either way, you'd eventually get the idea that 6 is the length of x. So 6 times 2 is 12. That's the same as 3 times 4. Another less numeric problem down here, so more traditional proof, is also written for you. So it shows your original picture. You have intersecting chords. I went ahead and I just drew in AB and CD, simply said to make triangles. Vertical angles are congruent. This is a little bit new, but makes sense. 3 and 4 are now inscribed angles that share the same arc, so they are congruent. Angle similarity with the triangles, and we're bringing this back, corresponding sides of similar triangles being proportional. So I chose AE compares to BE, the same way that CE compares to DE, and then cross multiplied. You'll be expected to do a little bit with proof, but for the most part, we're just going to be solving for the values of x. So a couple more problems here. So some things I noticed, I had congruent markings, so now these are both x. Oops, sorry. And then I can either set up the triangles and solve from there, or skip to the theorem where I can multiply a piece up until the intersection times the other side, and set that equal to a piece up until the intersection times the other side. So I ended up getting 36 is x squared, so we know x has to be 6. This one, they're trying to trick you a little bit. Don't be fooled. So you have x here, 5 here. I can multiply those. And they're technically giving you the radius here of 5 and a little bit more. So we're going to use that little bit more. So I go up until the intersection. So 7 times 3. Then we can cross multiply. I'm bringing back a problem. This is called a big circle problem that reviews some of the angle properties we've already done. So we have an angle bisector. So AP comes through and bisects angle BAC. We have a tangent, so it hits a circle once. And then this ratio of angles. So it says that angle ACB, angle CAB, and angle ABC are in a 4:3:2 ratio. Well, here's the deal. I know it's in a triangle, I can think of those as each 4x, 3x, 2x. They're angles, so up to 180. So I went ahead and I found that x was 20, and I plugged in those angle measures. I split this angle in half because of the bisector, and then I went after some of the things they're looking for. So they're looking for angle ABC, which is 40, arc B to F, which I found by looking at the inscribed angle across from it, it will be twice that amount. Then they started talking about angle BEP, random inside angle. I don't have a name for it. It's not central. It's not inscribed. That's where I could outline. Let me see if I have the tool. I don't know where the tool is. So I could outline the arcs across. So I'm going to say I have this arc of 60 plus across from the other side of the angle, 80, across from the 40 for the inscribed angle. Add those together and divide by 2. That's the rule for the random inside angles. So that was 70. And then they want this angle out here, P. So I look at where does it hit. Okay, if I follow along here, I start here. This arc is 160. I believe that it gave that to me. Or did I figure that out? Oh, no, I figured it out from the inscribed angle of 80 there. And then I can take that length, 160, and look at the other part between it, the other arc for that angle would be 60. I subtract those and divide by 2, so I got 50. And then lastly, they wanted me to find angle PBC, which I'll remind you is a tangent and a chord angle. Therefore, it is half the measure of the arc right here that it intercepts. So I already had this piece of that arc. I know this piece, though, is going to be double the associated inscribed angle. So technically, the arc was 120. Half of that leaves me with 60. All right, guys, I'll talk to you soon.